Welcome to my session. I'm going to talk about high-throughput streaming Lakehouse with Apache Hudi. The conflict between streaming speed and data lake scale raises many challenges in modern data world. That is why we need streaming data lakehouses. With Apache Hudi, many of these challenges have been addressed with streaming-first designs. In this talk, we will dive into some of the key designs in Hudi and understand why Hudi is suitable for you to build a high-throughput streaming lakehouse. A brief introduction of myself. My name is Shiyan Xu. I'm a founding team member at Onehouse. I currently serve as a PMC member of the Hudi project and lead the development of Hudi RS, the Rust implementation of Hudi. I'm a co-author of the already book Apache Hudi, the Definitive Guide, which is expected to be published this November. Now let's establish a 10,000-foot view of how Hudi is defined as a comprehensive lakehouse platform. A lakehouse starts by storing a vast amount of data on the storage layer. Think about Amazon S3, Azure Blob Storage, Google Cloud Storage, and HDFS, with data stored in file formats like Parquet or ORC. At the core, Hudi defines a table format. The table format describes table layout. It means it defines what metadata needs to be stored and maintained to properly describe the raw data files stored in the base path of a Hudi table, and also defines how the metadata structure looks like. This is the key component that ensures raw data can be efficiently manipulated by all kinds of read and write operations. Building on top of the table format, Hudi implements the storage engine. This is a transactional database layer that understands the Hudi table format and delivers essential lakehouse capabilities, such as indexing, which means indexing can be like having an incoming record, and you identify which file on the storage contains that record. Or it can be optimizing a SQL query that contains predicates so that you can skip files and get results efficiently. The storage engine also contains table services, which is about optimizing the table storage. We will cover that in more detail later. And also include concurrency control mechanisms, which we will also spend time and discuss more detail. So when it comes to data ingestion, Hudi seamlessly integrates with different execution engines such as Spark or Flink. These engines is able to plug into various data sources and pulls the data from them and writes to the lakehouse in Hudi table. Because of the integration, those engines is able to understand the table format and able to leverage those storage engine capabilities to implement data lakehouse features. And to make the data universally accessible, Hudi implements catalog sync mechanism. This mechanism is able to register Hudi tables with multiple data catalogs, which enables a wide range of query engines, which unlocks the data for all kinds of analytical queries. Hudi also provides platform components to help you properly manage thousands of tables often found in large data platform. For example, you might need a CLI tool to inspect or print out some critical information for multiple tables so that you can make some inspections and troubleshoot production issues. So with this structural overview, let's move on to Hudi's specific design that enable high throughput streaming. We will be discussing 5 of the key architectural designs that make Hudi well suited for streaming use cases. I will cover the first 4 designs briefly, giving you a high-level concept for each. Then we will delve into the design details for the last one, Hudi's non-blocking concurrency control. This is critical for achieving true high-throughput performance in lakehouses. Firstly, I want to draw your attention to this table layout showing what the Hudi table is consist of on storage. Among other metadata directories and files, a Hudi table primarily stores the data in the base file and log files that is circled in red. These base file and log files are physical files. Hudi also defines logical grouping called file slice and file groups. Let me break down this for you. Base files are typically in columnar file format like Parquet, which store the primary data for this table. Log files contains changes to the associated base files. So logically, Hudi groups one base file with multiple log files into one file slice to represent a version of those records at a given time. So a file slice is always associated with a time. And because records are changing over time, Hudi uses new file slices to represent the new version. So the same set of record in one file slice can change over time and be served through a new file slice corresponding to a new timestamp. So all these file slices all belong to the same file group. So that's why file groups, file slices, they are logical concepts to group physical files. With this understanding, let's talk about table types. Hudi defines 2 table types which have very different performance characteristics. First, we have copy on write, or cow table. When processing updates and deletes, cow table rewrite the base files to serve the latest version of those records. There isn't any log files in cow table. Second, we have merge on read, or MOR table. Instead of rewriting base file to represent new version, MOR table buffers updates and deletes in log files alongside those base files. In order to read the latest version of the file slice, the Hudi reader must be able to merge the log files with the base file on the fly. MOR table runs, you can run separate compaction jobs on MOR table so that it merges the log file with the base file to create a new version. So as you can imagine, cow table are pretty efficient for reading after it creates a new base file, because the base file are usually in columnar file format, which is optimized for analytical queries. But it incurs high write amplifications. Let's say there's one record in one base file has been updated. That base file could contain thousands of records as well, but because cow table needs to rewrite that base file, you are rewriting the same set of thousands of records. Although they have not changed, only one of them is changed. So this means there are high write amplification. But in MOR, all these changes, the changes of the record are buffered in log file, which is being appended on the storage. So MOR can absorb large volumes of updates and deletes with minimum write amplification. This is why MOR table is very suitable for streaming write scenario. The second design is about efficient writer indexing. To perform efficient updates and deletes, Lakehouse writers must be able to quickly locate the records in the table. Hudi pioneered record-level indexing in Lakehouse space. The indexing component directly maps incoming records two specific file groups within Hudi tables. By doing this record indexing lookup during the writes, incoming record can be deterministically routed to their corresponding file groups based on the record keys. In high-frequency streaming update scenario, the capability of efficiently finding the right file group directly determines the overall write latency, because you need to perform an indexing process and then write the record accordingly. So the indexing process is an important segment of the overall write process. So having a record level indexing, which is a very efficient process, is a critical step of running a high throughput streaming pipeline. The third design addresses a major challenge in streaming: small files. High frequency streaming writes inevitably creates a large number of small files. And this is a top performance killer for any lakehouse. Small files makes everything slow and cumbersome. To address this, Hudi designs auto-file sizing mechanism. During the write process, Hudi uses a bin packing algorithm to assign incoming records to their corresponding file slices based on a configurable size criteria. On the right side diagram, you can see there are three examples of file slices. The first two, they have been identified as small files because the green sections indicates the current size of this file slice, while the white section and green section together indicates the total target size. Let's say 120 megabytes is the target size we want to maintain for these files. Because they are less than 120 megabytes, these files are identified as small files. While in the third file, because its current size is already close to the 120 megabytes, it's being identified not as a small file. So by doing this kind of assessment, Hudi writers is able to assign different new records to these file slices so that they are being packed into those file groups to maintain to try to stay closer to the target file slice, the target file sizes. So essentially, this process works to proactively fill up file slices that would otherwise be classified as small files. Therefore, it helps maintain an optimum target file size during the write itself, addressing the small file issues effectively. The fourth key streaming design is the support of async table services out of the box, which further addresses small file issues. Table services are maintenance jobs for Lakehouse tables. Table services do not write new data. Instead, they optimize the existing table in terms of layout and storage efficiency. To handle small file issues, Hudi supports compaction and clustering. Compaction performs the merging between log files and base files, while clustering specifically rewrites small files into larger ones. Streaming writes usually demands low latency, like in real time. Only by running these critical maintenance jobs asynchronously, without interfering the ongoing writers, then can we truly achieve an efficient and more real-time streaming lakehouse. Now, the last key design for streaming that I want to primarily focus on today is the non-blocking concurrency control, or NBCC, introduced in Hudi 1.0. You might be asking, why do I say don't be too optimistic? It is because most Lakehouse frameworks today relies on optimistic concurrency control, or OCC. In the following slides, I will illustrate why you should choose Hudi's NBCC over the traditional OCC for high-throughput streaming use cases. Historically, we have been used data lakes primarily for batch jobs. The go-to method for handling multi-writer scenarios has been OCC. But are we being too optimistic? Imagine two writer processes, an ingestion writer producing new data every minute, and a deletion writer enforcing GDPR compliance, taking much longer time to find records and issue the deletes. These two jobs are likely to overlap on writing files because of the random deletes. You don't know which record you are supposed to delete, and you don't know if the next ingestion run would be actually updating a past record. So you can anticipate when the conflict would happen. But because of OCC, when conflict happens, one of the writer has to abort and retry. And the same thing could happen next time. So this could lead to the deletion job being into a starvation phase. Actually, OCC was designed for append-only workload, but it is not suitable for streaming and handling changes. OCC optimistically assumes contention never happen, but in reality, it happens quite often. So when it happens, there are consequences. A batch job running for hours could fail at the last minute due to a conflict, result in a lot of costly resource wastage. In database terms, this is like mixing long-running transactions with optimism. The longer this transaction runs, the higher the probability they will overlap and conflict. Let's look more closely at how OCC works. Conflicts happen when multiple writers make updates on the same file group, as shown in the red boxes. By using OCC, writers will need to acquire a lock and check for conflicts before committing the write transactions. Let's say writer 1 grabs the lock first. Because writer 2 hasn't completed its commit, there is no conflict for writer 1. So it can successfully complete the transaction. But for writer 2, when it grabs the lock, writer 1 has already committed its change. Therefore, writer 2 sees there's a conflict and will need to abort and retry. This causes delay and wastes compute resources. Obviously, this impacts the overall write throughput. Now let's look at the alternative, Hudi's NBCC. The core advantage here is that there is no retry. The conflicting updates are allowed to proceed by saving the record into different log files within the same file group. The critical mechanism here is to use locking upon the time generation. This locking allows us to write the records into separate files and introduce only a negligible delay, normally less than, let's say, 50 milliseconds. The resulting log files follow a strict serialization order based on the commit completion time. This is critical because during any subsequent merging process, the records need to be ordered properly, and then the merging can be done correctly by following user-defined merging semantics. What I mean by this is, when you merge two records, you have to find the ordering of these records. So you need to look at some field of the record, then decide which record is the newer version, which record is the older version. So when you do a merging, you could pick the newer one, or you can do a custom-defined logic to get the merged results. So that's why ordering is very important. And by following the completion time to enforce the order of files, and then follow the ordering value of the records, then you can perform merging correctly. As you can imagine, by avoiding retries, concurrent streaming writes can achieve much higher throughput in your Lakehouse. Now that we understand NBCC's advantage in improving throughput and saving resource wastage, let's dive deeper into its design by understanding the building blocks that make NBCC possible in Hudi. The main building block is Hudi timeline, which is essentially the transaction log of the table. It records all the actions that cause changes to the table. There are actions performed by, for example, upsert operations, or by table services that rewrite files. This is the core component that allows Hudi to provide transactionality for the Lakehouse. All action transitions through several states, moving from requested to in-flight, then to completed. The timestamps associated with these states, especially requested and completed states, are very critical. The requested time indicates when an action started, and the completion time indicates when it's successfully finished. For Hudi writers, they can only fire off commits in parallel when they have unique requested time. For readers, as we just described about the merging semantics, they rely on the completion time to have a deterministic order and do a correct merging to get a reliable output. This is especially important to handle out of order data. Now there's a problem lies in this process. How do we generate globally unique, monotonically increasing timestamps across all writers, especially when they are running in different servers or across data center regions? Let's discuss this next. So we are facing the issue of reliable time generation. Different servers can have clock drifts, which can result in conflicting timestamps. To maintain the integrity of Hudi timeline, we need a reliable way to generate monotonically increasing timestamps for all concurrent writers. Hudi fulfills this requirement with a TrueTime-like mechanism, inspired by Google's Banner. Here is how it works. Let's assume there's a maximum clock drift between writer 1 and writer 2, which is less than X milliseconds. When writer 1 needs to generate a time, it requires a lock. Then it generates the timestamp using its local clock. Then it sleeps for X milliseconds before releasing the lock. This intentional delay, it's meant to account for the worst case clock drift to prevent other writers for generating a timestamp within that window. Now, if the writer 2 was waiting on the lock, it can now acquire the lock and generate its own timestamp and follow the similar process. So this synchronization mechanism ensures that timestamps generated by all writers are always monotonically increasing, solving the distributed lock drift problem, which is super critical for NBCC. Let's discuss the third building block, leveraging the log structure merge tree for the Hudi timeline itself. With high-frequency streaming writes, there will be a large number of commits recorded in Hudi table. The question is, can we store all these commits efficiently while supporting long commit history for inspection and auditing purpose? In Hudi 1.0, timeline is implemented as a log structure merge tree. In the active instance layer, as you see in the top layer, commits are stored individually for fast read and write operations. When the number of active commits exceed a configurable threshold, they will be flushed to the next level as timeline segments. This process is called timeline archival. These segments include multiple commits into one file and sort them by time. And because they are all sorted, looking up a past commit can be implemented very efficiently by using binary search. You can even further compact one level of the segment into the next level of larger segments for better compression ratio. So with this LSM timeline, the large number of streaming writes to a Hudi table can be handled efficiently without running into timeline loading overhead. Imagine if you are running a one commit every minute, and the table needs to run, is designed to run 10 years for auditing purpose. You have to keep all the past commit for 10 years. That means you need to write more than 5 million commits in total, because there are 3 states, which means you have 15 million files stored in a directory. If you don't do this optimized storage, your file system wouldn't be able to efficiently load the timeline commit files. You will not be able to efficiently find the commits you want. So with this LSM timeline, Hudi table can handle this workload and ensure Lakehouse scales to high throughput streaming. Finally, let's put NBCC in action and visualize the whole process. Imagine we have 2 concurrent writers, writer 1 and writer 2, both updating records within the same file group. Because of NBCC, they can both proceed without blocking. They each write their own updates into separate log files. Each file has timestamps. They are associated with distinct requested and completed timestamps. To guarantee that files themselves never conflict on the file system, the log files are also named distinctively with a writer-specific suffix. This guarantees there's no overlap on the file name. Now let's look at the compaction service. At time T4, we schedule a compaction. This service, the compaction service needs to select log files to merge with the base file and create a new version of that base file. What is important here is only those log files whose completion time is earlier than or equal to the compaction time T4 should be picked for the current merge. For instance, on the other side of this example, the log file that completed at T5, which is highlighted in red, there's a log file with starting T2 and end as T5, will not be included for this compaction, although it was started as T2. So that log file will be considered for to be grouped as another file slice. So this separation and serialization using completion timestamp ensures the transaction integrity and is the building block for implementing NBCC. And then, therefore, you are able to achieve 0 retries for your streaming pipeline. So to recap, streaming write scenario have real challenges for lakehouses, which is why Hudi was built with streaming first designs. Let's quickly summarize how Hudi addresses these challenges. For frequency updates, Hudi leverages MOR table type to absorb changes quickly into log files. This minimizes the write amplification. For large volume of mutable workload, Hudi uses efficient record-level indexing to locate record fast and improving the overall write latency. When small files proliferate, Hudi can deploy auto file sizing and async compaction and clustering to optimize the file layouts without impacting write performance. When concurrent updates run into conflicts under OCC, Hudi uses NBCC to avoid costly retries. Finally, when accumulating long commit history in streaming writes, the timeline the long commit history can add read and write overhead in the timeline. Hudi implements LSM timeline to optimize the storage and loading performance. Overall, all this streaming-first design make Hudi a robust Lakehouse platform for high-throughput streaming use cases. Thank you very much. Yes, question?
Quick question about the auto file sizing. Is this feature supported in the Hudi integration?
Yes, it is a generic feature being implemented into the right path.
In which version?
I don't remember exactly the version introduced. I think it's been there for quite some time.
Okay.
Yeah.
So which means that different checkpoint, you can continue write the same file, a big file.
You can continue. It only assigns new records into the. Let's say you are updating a file group, and along the same batch of updates, you have some new records. Then it can assign those new records to the file group when the file group is determined as not that much size comparing to the target file size.
I see. This is for upsert.
Yeah, it only works with upsert or insert operation. Yeah. Yeah.
So when you're generating the timestamps, you're still locking on something. So how is that not blocking still?
In terms of blocking, it's more like you're comparing what kind of blocking you're talking about. So it will block for a short period of time to generate the time, the true time,
Okay.
but it's like kind of negligible because when you account for clock drift, it's more like 10 or 20 milliseconds. That's like the worst case. So, and most of the time you won't have that many of multi-writers. It's typically like 2 or 3 or 4 in the Lakehouse like writing scenario. So if you consider this kind of locking among a few of these, it's not like a significant blocking. It's more like when you need some timestamp, you lock and generate the time. Usually you call some system function like current timestamp, and then you can release the lock. So it's not like a long process.
Okay.
Yeah. Any other question?
So it's actually, I'm very interested about the scale testing of the Flink Hudi upsert use cases. From all the use cases, like in the industry, do you have any data on that part?
I don't have data by my hand.
Okay.
Yeah.
Probably later, when we will invest on that, we can get some data.
Yeah, of course. Looking forward to it. Okay. Then I think that will be it. Thank you for attending.